Hello everyone and welcome to Energyvisionary platform. Today we have a special guest with us and we're going to be discussing CHP technology and something I've been working on as well to help educate clients out there of all the different government grants, the different technologies and the different strategies. We want to showcase some of these technologies and give a high level view of the benefits and how you as a business owner can achieve your energy savings and maximize the different technologies that are on the market and that have been successfully implemented. So today I want to welcome Matthew Swinamer with CallitCut Energy, and today he's going to be discussing the benefits of combined heat and power generation, or CHP generation, and we'll ask certain questions that you might be thinking about this technology. So we'll get right into it. Matthew, welcome to Energyvisionary.
I got lots of time to hang out here, so this is a great way to spend my time.
Good. Glad we can have you.
Yeah, so I'm going to share my screen. Is that okay?
Yeah, definitely.
Well, yeah, I mean, just for framing the conversation, put together a bit of an agenda. And I'm excited to kind of just start with the conversation around some of the problems that we have with power generally. And I'm based in Alberta, Canada. And so a lot of the examples I use, a lot of the content, a lot of the numbers I reference are from an Alberta's perspective, but CallitCut does work all across North America. We have a big office in California, actually 4 offices in California, and we do work right across the whole continent. So just wanted to highlight that. So one of the problems with just generally how we generate power in North America is we use a lot of thermal power generation, whether that's coal or natural gas. And typically, the overall efficiency of that from fuel into electricity to your house is actually somewhere in the range of 30 to 32%. So we're losing a lot of energy along the way, which actually ends up increasing the cost, but also it ends up increasing the overall CO2 produced per kilowatt that's finally delivered to your house. Here in Alberta, we actually have relatively dirty power. It's actually 420% more CO2 output per kilowatt here in Alberta than the average of Canada. And that's just a reflection of the type of power generation that we use here in this province. One of the other problems we have is just the limitation of the grid. I mean, Aaron, you probably have experienced this a lot more than I have, but a lot of times a facility will need to be built in a particular area, or maybe they're wanting to upsize and they just don't have enough capacity from the grid at their current location or where they want to build their facility. Mm-hmm. And as a result, they end up they have to spend a lot of money to get those lines or to upgrade the infrastructure. And specifically here in Alberta, we actually have a very overbuilt system, and we actually end up paying on average 50% of our utility bill is actually the cost of just transmitting the power. It's pretty crazy. Right. My utility bill at home is somewhere in the range of 65 to 70% is my wires and administrative charges. I only pay 30 to 35% for actually the cost of my electricity.
Yeah, no, it's true. And a lot of our clients might be manufacturers, and yeah, definitely they think they can go build out where it's affordable on some land out in the country, and they go and they get their study completed and they don't have the power in that area. So now it could scrap your project or a big adder in cost to get that infrastructure built. So really good point there.
Yeah, and one of the major industries that really felt hard was here in Canada, cannabis is legal, and so we do a lot of cannabis manufacturing in indoor greenhouses, and they use a tremendous amount of power, and nobody thought that they'd be using as much power as they are. And there's examples here in Alberta where greenhouses or indoor cultivation was using tens of megawatts of diesel power on site within spitting distance of big wires like this because they just couldn't get grid access in time. So it's a huge problem that can happen. I have added some QR codes if people want more information. We do have videos on our website to these different particular topics. And so the third problem that, there's lots of problems, but the third major problem, and I don't know how relevant this is, Aaron, to a lot of your viewers, is remote power. But the reality is there are facilities and there are places all across North America where it is cost prohibitive to connect to the grid. Obviously in Canada, there's lots of examples of that, whether it's in the northern parts of Canada, but even sometimes there's simply the cost associated with supplying power to your facility. It can be very cost prohibitive. And this power, in fact, actually, I always find this stat interesting. So in Canada alone, there's 200,000 people that live in off-grid communities. Those off-grid communities pay for power in the range of $1 per kilowatt.
Wow.
So on average here in Alberta, people are paying 5 to 6 cents. That's just their energy charge. They're paying $1. So, I mean, it's tremendously expensive. And then because you're using exclusively diesel fuel, the carbon impact is quite high as well. So yeah, so those are just, I wanted to shape the conversation around power with some of those things. So let's get into maybe what is CHP. And what CHP is it's a technology that effectively generates power and heat, so electricity and heat from a single fuel source. And what we're effectively doing very simply is we're taking a generator and we are generating electricity for that grid. We're providing the primary source of power to that facility is the generator versus the grid. And we're taking heat off the generator and we're utilizing that in the facility to lower their heating costs. And overall, this creates a much more energy efficient process, as you can see on the screen, up to as much as 93% fuel efficiency. But it can also help increase the reliability of power to that facility, and it can reduce that facility's greenhouse gas output. So it can help become more sustainable. So those are kind of the main reasons: economics, reliability, and sustainability.
And I just want to jump in on this slide. So the photo looks like a barrel of oil, but in reality, that would be natural gas utilities that you have currently on your property that you would be tapping into to run essentially a large engine generator, correct?
Absolutely. Absolutely. I mean, I have a slide that gets to that, but a CHP could also be run on diesel. And like I said, it's effectively, this is proven technology. We're all familiar with generators. But what we're doing here, what makes this technology just that much more leading edge, is we're covering the heat off the generator, heat and energy that would have been wasted to the environment,
Right.
And we're capturing that and making it overall more efficient process.
Right.
So actually, here's an example of a design that CallitCut made for inside a specific building. And I love this image. I'd like to pull away the exoskeleton, but it really does help us show what is going on here. And simply put, like I said, it's a generator. You can see it right here. I'll use my mouse. You get your generator here in your alternator. And what we're effectively doing is, cold water is brought from the building. It goes through this heat exchanger, which is taking heat from the engine, goes up through this heat exchanger, which takes heat from the exhaust, and you get hot water going back to the building. So power being generated here, heat being generated here, and transmitted back to the building. So you brought up a great point, Aaron, the different fuel types. So again, CallitCut works in lots of remote communities. We have lots of remote generation facilities, and they run on diesel specifically. And there's nothing preventing us from recovering heat from that generator, from the exhaust out of the engine, and utilizing that within some sort of facility on site. But to your point though, 99% of CHPs globally run on natural gas, and it's purely economics. Natural gas is in abundant supply and very cheap right now.
And a lot cleaner than most people think it is.
Very true. Very true.
Yeah.
So there's different forms of natural gas that we might use. So in some applications, you might use a synthetic gas. You get a lot of this gasifiers. So it's a gas that'll come off maybe, so there's a lot of lumber mills that will allow their wood chips to effectively be gasified, which produces a synthetic gas, which can be burned in an engine. Biogas is the next big thing. You can take that off an anaerobic digester and run it in a generator. We do lots of work and have had lots of interest in the area of biogas, specifically in California. And then finally here in Alberta, being a oil and gas producing jurisdiction, there's lots of times where we'll have a waste gas that just, it's not economic to produce, or there's just not a pipeline in place. And so we'll generate power using flare gas.
Excellent. And on biogas, real quick, we also worked on a project where a resort was looking to basically put their food and scrap waste into a biogenerator and produce fuel that way. So definitely a lot of different options you can take, but you definitely have to learn about these technologies before you can really think to implement them in your facility or development.
Absolutely, absolutely. And we can help you guys look at the options around biogas. You have to be very careful with what generator you use for that, because there are some impurities in that biogas that need to be considered when you're choosing an engine.
Right.
So, the biggest question that your viewers and anyone watching this video and the people that are asking me, why would I install a CHP at my facility? And one of the major reasons purely is we're actually becoming so much more fuel efficient. So again, I think I've showed this slide already, or we've alluded to this, but you're getting as efficient as 93%, whereas the grid, if here in Alberta, we're using coal, which is producing a tremendous amount more CO2, by the time it actually gets to our facility or gets to our house, we've already lost almost 60 to 70% of that energy. It's pretty incredible. Some technologies are better. I don't want to just discount everything or whitewash it as all is terrible. Mm-hmm. But generally, this is the benefit of CHP, is we're bringing that generation to our facility, and we're able to realize that efficiency. And ultimately, that efficiency comes out in an economics opportunity. So we're saving money. And I specifically put on the chart two jurisdictions, and this is relevant to a lot of other deregulated jurisdictions. But you have Alberta and California. And here in Alberta, we pay on average somewhere in the range of 11 to 14 cents a kilowatt hour. California, on the other hand, are paying somewhere between 23 to 26 cents. Well, we can very confidently produce power for somewhere in the range of 7 to 9 cents per kilowatt, or that's $70 to $90 a megawatt hour. And so there's a major difference, what we call the spark spread, between taking power from the grid and generating power on site. But the final thing that we can help realize that makes this economic so much more attractive is that heat savings allows us to offset the cost of what we would have been using for a fuel source to provide heat to that building, which again, ultimately for most buildings is going to be natural gas. Some facilities run on propane, but Aaron, you correct me if I'm wrong, but like 99.9% of buildings in North America are most likely heated by natural gas.
Yeah, that's correct. Like the primary heating systems, if you're heating a pool, definitely off a boiler, natural gas is most likely the design in that property. So that's what we're talking about when we say the heat savings. It's your domestic heating that would go through a heat exchanger, or your space heating for that property. So yeah, absolutely. Yeah, good savings there.
So the second reason a lot of people are looking at CHP is there's a lot of sustainability mandates that companies are looking to meet. How are they going to reduce their CO2 output or their greenhouse gas emissions output? And here in Alberta, we actually, for every 1 megawatt of CHP installed at a facility, assuming that that heat is used all year long, you can see a carbon reduction of somewhere in the range of 3,000 tons per year. That's equivalent to about 660 cars taken off the road per year. And so when the carbon tax here in Canada goes up to $50 a ton, that is going to equal a significant amount of savings.
Mm-hmm. Yeah, that's a really good slide for sure.
One thing I like to compare. A lot of people really appreciate this slide. So Aaron, one of the things that one of the reasons I like to show this slide is I just like to compare the average CO2 output per kilowatt hour here in Alberta versus some of the benefits of CHP. And so for every kilowatt of power produced here in the province of Alberta, we're producing 0.53 kilograms of CO2. And that's specifically a function of the types of generation that we have here in the province. So you'll see that on the right, there's this giant, this big wedge of the pie, and that is coal power. And we're very quickly getting away from coal, but nonetheless, we still have a significant portion of our base load is produced from coal. And so as you can see on the graph there, that we're actually able to reduce our CO2 output using CHP by 47%, assuming we're using all of the heat of that CHP. And why is that? Because we're using a much cleaner burning fuel, which is natural gas, and we're able to effectively offset the fuel that would have been used in the building to provide heat.
Perfect. Yeah, no, that clearly, I think represents the advantages of producing on-site versus drawing from the grid. So yeah, no, that it makes perfect sense to me.
So what are some of the places where a CHP might be put in? Like what type of applications? And you can see on the screen, I've got a lot of different options here. And I've put a little Alberta sign next to all of the ones that I am aware where on-site power generation has been utilized or CHP has been utilized. And I'll be honest, Aaron, right off the bat, there's probably a lot of other categories and there's probably a lot of examples that I'm not aware of, but I just wanted to show this, that this on-site power generation has been very widely, and the C's next to them are applications or different types of industries where we have been involved, whether either we've supplied a CHP or a power generation system, or we're actively supporting it through maintenance. So yeah, lots of different industries have already adopted this technology, and yeah, we're excited to see a lot more adopt as we move forward.
Yeah, absolutely. Definitely a vast opportunity for this technology to help clients basically lower those utility costs and maintain a little more reliability for their systems.
Absolutely. Awesome. Well, without further ado, why don't we get into the case study that we were going to chat about, which is
absolutely.
Which is the cogen at Red Deer College.
Yeah, let's check it out.
So we were commissioned to build a 1 megawatt CHP at Red Deer College. And so what you're seeing on the screen is on the left is what it looks like on the outside. So this is a modular design. It's a skid-based design that we built in our manufacturing facility in Red Deer. And one of the benefits of this facility being so close to our manufacturing facility is we're able to build it a little bit wider. We weren't too concerned about transporting it. And that's allowed us to make this an incredible educational facility. That was one of the things that Red Deer College really wanted to see. And so this is quite a bit wider than your average CHP, but it really allows us to get in there and see around. And so this is a facility that's producing about 1 megawatt of power, and it's producing just over a megawatt of thermal energy. And that thermal energy is being used within the facility. So this has been a great addition to reduce their greenhouse gas emissions, but also be self-sufficient in terms of power supply. The generator that's used is a Siemens SG42HM engine. In ideal conditions, that generator can produce as much as 41% electrical efficiency, 92% overall fuel efficiency. This project is at a relatively high elevation. If I remember correctly, it's about 800 meters. So there is some derating associated with elevation difference, but still, overall, it's a very efficient engine.
Yeah, and if you have the space on your campus, definitely, like you said, take advantage of creating this customized modular where you can get in and walk around and service the equipment. Yeah, it looks great.
Yeah, so one of the things I wanted to highlight for your viewers is one of the biggest questions I get asked is, how do you recover the heat? And so what I've done here is I've taken the PNID, the process and instrumentation diagram. And I know you guys definitely can't read that. And to be honest, you probably don't want to read it. Nerds like me nerd out on PNIDs, but I wanted to kind of give you guys a bit of an overview of how we're recovering that heat. And so effectively there's a big box in the middle, and that's where that's the generator within that enclosure. And what we're doing is we're bringing in cold water into the generator, just like almost every generator has. It's called the jacket water. And that jacket water is coming into the engine, and it's drawing the heat away from the engine so that that engine doesn't overheat. And then we have this other heat exchanger down at the bottom. I've used HX as the acronym, but what that's standing for is heat exchanger. And this is the exhaust heat exchanger. And so what's happening is just like a car engine, it's producing very hot gas that's coming out of the engine, and it's going into that heat exchanger, and then out the heat exchanger to our silencer, which is then being rejected to the environment. And then we're bringing that jacket water through. So you can see how the arrows are trying to indicate temperature differences. So you have cold water coming through. It's now been heated up a little bit.
Mhm.
And then it comes into this heat exchanger here, which then takes it again. You adding more heat here, and the temperature rises through the heat exchanger. And then it comes to this heat exchanger here, which is called the CHP heat exchanger. And this is where we transfer the heat from the CHP to the building. And so I'll just pull up the last arrows. So then on the other side of the heat exchanger, we have cold water coming from the building through this heat exchanger and then going back. So this is called a plate and frame heat exchanger. And it's a water to water heat exchanger where we're transmitting heat from the hot side to the cold side. So typically on all heat exchangers, you're gonna have a hot side and then a cold side, and hot side. So we're transmitting, and these heat exchangers can be very, very efficient. So then obviously that cold water comes back through and it goes back into the generator. So then how is the heat then being transmitted from the CHP that you saw in the photo before to the building? And so on the outside of the CHP, you'll see these two insulated lines here. So what we've got outside the modular enclosure is these two 4-inch lines. I know those don't look like 4-inch lines. They've been insulated because here in Canada, we get down to minus 35 degrees Celsius. So they need to be insulated. And so we've got two 4-inch lines. So this should be, one's the supply, I believe this is the supply and this is the return line. And supply to the building and return back. And so it's a 4-inch line with 3 inches of insulation to get a 10 to 12 inch outside cladded line. And effectively what's happening is that CHP heat exchanger that we saw on the previous slide, we've taken the heat from the engine and the jacket water, it's been consolidated, and now we're taking this and we're flowing that fluid back through the heat exchanger and back to the building. The heat loop at Red Deer College is actually I think it's 1,500 feet long, like the whole loop. Oh, wow. So it's an incredibly long loop. And so then on the building side, we have another set of heat exchangers where we are transmitting the heat from this intermediate loop to the building loop.
Excellent. And that's all, like you said, in our cold climates, and to prevent the heat loss, that temperature or the fluid medium is mixoglycol, correct?
Yes. Yeah, typically we do 50-50 glycol water.
On the heat exchanger side, and then the building loop, because it's in the building, could be just treated water for closed
Absolutely.
loop system. Okay.
Yeah, in a lot of our applications, our heat exchanger is in series with the boiler, and literally the water that comes through the heat exchanger into the boiler ends up being consumed at the facility. So yeah, you definitely don't want to put glycol in it.
Yeah, yeah. And so with the preheat temperatures, how much is that boiler even running, if ever, right?
Great question. So we can take the fluid up to 90 to 93 degrees Celsius at the high end. Mm-hmm. So depending on what temperature your boiler set, that boiler might not need to do any more work, which is what Red Deer College is actually seeing when this CHP is operating. They're definitely seeing a significantly reduced demand on their boiler system. Let's actually look at what this facility looks like on the inside. And CallitCut, we did a 360 view of the facility itself.
Oh, wow. That looks great.
Yeah. So what we're looking at here is, here's the engine. As I showed you, here's the alternator. So here's where we're generating 480 volts power. So approximately 1 megawatt being generated. And as I showed earlier, so this is our exhaust heat exchanger here. And you can see the exhaust coming out of the engine here. And so as I showed before, we've got the jacket water is coming through the engine, taking the heat from the engine. It's taking about 500 kilowatts of heat from the engine. And then it's coming up through these lines here. It's going into the shell and tube heat exchanger. It's taking heat from the exhaust. It's taking it from about 450 degrees Celsius down to 120 degrees Celsius. So there's a pretty big temperature change
Oh, yeah.
on the exhaust. And we're taking the temperature of the water from about 60 degrees to 80 degrees. Really does show you how much more energy there is in water,
Yeah.
water temperature rise, than there is in exhaust. So here, I'll just zoom in a little bit closer so you can see what's going on. So as I said, you can see there's the exhaust coming out of the engine, coming up and into, now this here, for those of you that are interested, this is an exhaust bypass. So let's say the facility doesn't need the heat. Well, we don't want to superheat, or we don't want to boil the water inside this heat exchanger. So we go to the bypass mode, and so it goes straight from there through the bypass and out to our out to the silencer on the outside. So I talked about how, and I'm just going to scroll to the other side of the engine so you can see. Actually, while I'm here, so here is our electrical panels. So this is called the switchgear. And so this here is the engine control panel. This is what's controlling and monitoring what's going on. And by the way, we can actually do this remotely. I could pull up the viewer for this CHP and see how it's doing and see all the parameters. And then the other couple panels are the panels that are synchronizing the power from the generator with the power from the grid and then transferring it to the facility.
Very clean job. Looks great.
Yeah, it does, doesn't it? And then I'm just going to the other side. Mind my navigating. So like I said, this is a very wide facility. You wouldn't normally have this much space. This is a real blessing, especially for our mechanics who have to go in and do maintenance on this. Okay, so what are we looking at here? So we're on the other side of the engine, and what we're seeing here, this is our makeup oil tank. So the nice thing here is you have this nice sight here that tells us how we're doing. So we're starting to get a little bit low on our oil. Reminds us to come in there and add some more oil or do an oil change. And here, this is the plate and frame heat exchanger. And I'll zoom in here in a second, but what's happening here is that consolidated heat from the jacket water and the exhaust comes into this heat exchanger. And this is where the heat is then transferred from the CHP loop in this facility here. And it's transferred through to the intermediate loop. So let me zoom in so you guys can see. And this is, as I said earlier, this is a plate and frame heat exchanger. I actually built one of these in university. It's really, really boring to build because it's a series of plates.
With the gaskets.
Exactly, yeah. And you want to make sure you get them right, because if you put them on one wrong way, I mean, So as you can see here, if we wanted to add more flow, what we would do is we'd take this plate off here and we would just add more plate, more gaskets and more plates. So you can see here, this is the heat coming from the exhaust, coming down and into this plate frame heat exchanger. And I'm sorry, I can't show you guys from a good angle, but you have the building supply and return lines down here, which are coming into the bottom of this heat exchanger. And that is how the heat goes from the CHP loop to the building loop.
Excellent. And as far as a building control or automation standpoint for a client, they would have access to see, the system live and it actively working. Correct? Is that the dashboard you're referring to?
Absolutely. So this particular system, we use a COMAP controller. And with that, we can monitor and control the engine, and we can monitor all the other sensors within this facility. We can monitor, and we can historically chart that as well. Other systems, we have the ability to see how much heat we're storing. This particular facility doesn't have BTU meters on the heat exchanger plate. But yes, there's a lot of abilities to integrate the controls, the system with a facility's BMS or building management system.
Excellent. And obviously the programming of this would all be automatic. If there was down for service, it would switch over to, the grid or your boilers.
Yep.
That would be all part of the control system, part of the package.
Absolutely. Yeah.
Excellent.
So part of the controls programming, we sit down with the client, our electrical engineers determine what's the order of sequence that we want. So does the generator come on first, or we draw power from the grid, and how do we do that? So it's a very interactive process with the clients, facilities engineers or facilities people, and our programmers. So I didn't want to get too deep into the design of CHP, but one of the things I did want to talk to is some of the high level things that we consider when we're designing a CHP. And it really does depend on the level of complexity that we want to go. And I guess my slide transitions haven't been working appropriately. But one of the things I wanted to show here is that we typically start with CHP is designed around the engine. And then from there, we're going to determine the right power generation alternator. So what voltage is your building at? What's the right voltage to be operating? Are we 480, 600? Are we medium voltage? Are we 4160, 13.8? Are we lower voltage or higher voltage than that? And then we start looking at heat recovery. And then we start to get into some of the fancier stuff where does your facility not need heat, but actually need chilling? We've been looking at some data centers where they don't need heat, but we could take that heat and put it into an absorption chiller and produce chilling. And then for some of our greenhouse applications, they actually look at CO2 recovery. And so there's a lot of levels of a design complexity based on each application. Then on the right side, there's the integration with the facility itself. So, and meeting the requirements of the jurisdiction that we're in. Different jurisdictions will have different emissions requirements and different regulatory regimes. For example, California and Ontario, for example, have much stricter emissions limits than what we do here in Western Canada. So it's something you always have to consider. Power synchronization. How are we going to synchronize that power with the grid and then transmit it to the facility itself? Physically, how are we going to mechanically connect the heat from the CHP into the building? I did kind of talk to that in the previous slides. And then regulatory, there's a lot of regulatory aspects to these projects, and making sure that we're in line with current legislation and legislation to come is definitely a huge item to consider.
Right. So just for this overall topic, we're giving, the viewers here ideas of what is possible
Absolutely.
for their development or property. There are different steps, but that's why you would bring on, us as consultants and professionals like Matthew to go through and do that due diligence to get the best project for your needs. So yeah, it looks like a lot, but this is what we do for a living. So you're in good hands.
Well, and absolutely, to your point, Aaron, like when you and I go away and support someone with a feasibility study, which we can get into here shortly, these are some of the things we'll consider for you guys to make sure that when you guys move forward with a project like this, or if you move forward, that we're making sure we've ticked all the boxes and nothing's going to surprise us at the end.
Yeah.
One of the biggest questions I get at this point, if someone say, yeah, I like what you're saying, we're going to save money, we're going to reduce our CO2 consumption, and we're going to increase our reliability of power on site. What's the next step? What's that first step? And so really at this stage, Aaron and his team and my team here at CallitCut, we're going to want to look and understand your facility energy consumption. What are you consuming on a monthly, seasonal, annual basis, but what are you also consuming on an hourly basis, whether that's in the middle of the day or at nighttime? And from that, CallitCut can do a very high level feasibility study for you guys for free. That's our gift to you. And then from there, depending on the results of that study and what you guys think, we can then move into a much more in-depth engineering study, where at that point we'll size out a CHP, we'll do that sort of a review, we'll then physically go and install it to your building, and then at the end of that, we're going to have a long-term maintenance agreement with you to make sure that that equipment is being taken care of.
Yeah, and then on the consulting side, obviously on the design, like you mentioned before, how does that integrate physically with the building's electrical systems and natural gas systems? So that's where we would come in on the design side and provide full construction documents so that you can tender out the installation. Because CallitCut would supply that equipment, provide, like you said, the maintenance on it, but they don't necessarily complete the installation of the services and the piping throughout the property, correct?
Absolutely. Yeah.
Excellent.
So as I said at the beginning, Aaron, I know that you have viewers from all over North America. The major area that I operate and that CallitCut operates is here in Alberta, and I know that in lots of jurisdictions there are lots of different types of grant opportunities. But I did want to highlight 3 or 4 active grants here in Alberta. And I know that you know a lot about these, Aaron, but right now here in the province of Alberta, there are specifically 3, potentially 4, definitely 3 grants available that CHP is definitely applicable. It meets the technology readiness level and it's shovel ready. And so the first one, which is already expired now, is the TIER, i.e. Industrial Energy Efficiency Grant. But that was up to $20 million per project. These CHPs are typically under $20 million, so and up to 75%. And then some of the other ones that are still open is the one through ERA. That's up to so funding amount is between $2 million and $15 million. And then the one that's probably the most relevant to your average sized CHP or combined heat and power system is the one through Alberta Innovates, which is again through Alberta's TIER program, which is offering up to 75% financing for shovel-ready projects, and they're willing to support a project within the range of $200,000 to $5 million.
Excellent. Yeah, and just to add to the point of these grant opportunities, definitely feel free to reach out to us if you have the funding in place and a project. That's what the shovel ready means, is that you have already taken steps on preliminary designs, you have funding in place, you submit this application and you will apply to get a portion of your project paid for reducing those emissions. So definitely take advantage. And like I said, through energyvisionary.com, we're constantly populating any updates on grants or funding that the government will be putting out. So we're definitely going to be seeing a lot of that from the federal and provincial and municipal levels to help stimulate the economy going forward, for sure.
So who is CallitCut? And you know, we are a very innovative company, and we've been around for close to 30 years, and in a couple different iterations. But CallitCut is a solutions-focused company that's really based around engine-specific applications. So we've been building compressor packages and power generation equipment and combined heat and power systems for well over 30 years, based predominantly out of Red Deer in Canada. And then we have 3 or 4 offices in California. And you know, some of the things that we do is we provide design. Oh, no, my videos aren't playing. Oh, there they go. Design, manufacturing, and service support. So I love this slide. What we're seeing on the left there is a diesel generator that was designed. You're seeing in the middle it being constructed. And on the right, unfortunately, is not the one that's being manufactured. That actually is Red Deer College again. But I love this slide. I love seeing that engine go in.
Yeah, that looks great.
Yeah, cool.
And then as far as your role, we didn't really touch on that, but
yeah.
Maybe you could speak to how a client interacts with you along the way of getting this completed.
Here's my contact details. My job is to see if CHP or on-site power generation makes sense for you and your business. My goal is to see you guys save more money, reduce your utility costs, reduce your CO2 output. And the first real stage is me looking at your utility bills, looking at at what you guys are consuming in terms of power, and seeing if we can come up with a way of helping you guys realize those opportunities through CHP. And I'll be honest, you know what, there are times where it just doesn't make sense. And we want to make sure we get you to that stage as fast as possible.
Excellent. And just for obviously the way things are right now, we're filming this during COVID. So depending on what type of lockdown, obviously, I'm sure Matthew would prefer to meet for a coffee or meet in a boardroom. But just like the format we're in right now, Zoom calls might be the way, or Teams might be the way to do it. So definitely reach out to either myself or Matthew if you're interested in getting that first step completed. Is it worth it for your property or development? So
absolutely. Yeah, you're absolutely right. Like I love meeting people in person. I love going to people's facilities. I love getting to know what people are doing. It's so cool, Aaron, and I know you get that experience as well, but one day I'll be in a food processing facility. The next day I'll be in a greenhouse or a manufacturing facility. And it's just cool to be able to see all the different types of industries and ways we can help.
It is, and I agree. I like to walk the property as well, get a sense of location. We didn't really chat about this, but during our feasibility walks, we look at a variety of options for a location to put this CHP. And obviously we do consider who are your neighbors, you know, environmental. If you're in a national, you know, we've had clients that are in national parks, and they've installed these. So definitely something, you know, maybe you could speak to is the footprint, and then possibly the noise that someone might say, well, it might be too loud for my community.
Yeah, that's a really good question, Aaron. So CHPs can come in all shapes and sizes. I'm going to go back to this guy here because I think this does a really good job at showing. So I showed you a Red Deer College's facility was intentionally designed to be wider, but we can have what's called a skin tight unit that can be as narrow as 6 feet wide and 8 feet long. And we have them. In fact, Chinook Mall has a very small, actually, I bet you I have a photo of that one. I don't believe, actually, no, I don't. I don't have a.
But to that point, Chinook Mall is right in the middle of a community, and you know, absolutely. No complaints, and it's just part of the you know, system for that property to operate.
Aaron, I've been going to Chinook Mall since I was like 3 or 4 years old. I would walk to Chinook Mall. I used to live in Mayfair, and I did not know that that Chinook Mall doesn't have but one CHP. They have 4. They have 4 CHPs in the mall. Wow. So you would never know. You would never even know where they were. But yeah, we fit them in utility rooms, and so they can be very small. So you can have very condensed units. We can build them inside the unit. In fact, we get asked all the time, can we actually build a CHP in the room? And absolutely we can. We can break an engine down, haul it into the space, haul it upstairs. And so CHPs can be very easily installed in relatively inconvenient places. And that's part of that feasibility study that you were saying. Is can we actually do this? Is there a place to put it? If not, well, let's call her a day. But we've done some pretty cool things.
Yeah, and similar to, you know, a lot of, if not all, apartment buildings downtown that have emergency generators, similar code applies for a CHP inside a property as far as fire ratings go, sound levels, and life safety on that front. So yeah, definitely part of the first step is, you know, where can we put this piece of equipment?
Exactly. And sometimes the roof is, what you're seeing here is a 265 kilowatt unit in Edmonton. You can see the Stantec towers in the background. Oh yeah. And that's on the roof of an office block. And then right across the road from it, we have a 600 kilowatt CHP that's in a boiler room. So again, they in a multi-family dwelling apartment tower. So all shapes of sizes of CHP and all types of applications.
Yeah, definitely worth to check it out. If you do have a sustainability or a goal with your company to lower those emissions or lower those utility costs, CHP is definitely a great option to look at to make a big dent in that goal for sure.
Absolutely.
Yeah, so I think we touched on this a bit as far as placement of this unit in a property and the concern of noise levels and possibly even smoke. That might be one idea out there, that these might be too loud and too smoky for a community, but could you touch on that?
Yeah. Let me just pull up a quick slide. Let me go back to the Red Deer College. So this package here, it is within 50 meters of residence on the Red Deer College property. And to my knowledge, there has been no noise complaints about this facility. So relatively close with very minimal noise. So this unit itself produces noise. It's been mitigated down or attenuated down to 75 decibels at 10 meters. And that's a typical standard. So somewhere in the range of 65 to 75 decibels is what we design these systems to. And I'll be honest with you, they're no more louder than your average chiller on the roof. I've been to a lot of facilities where I'm getting drowned out by not by the generator that's on site, but the chillers that are on site.
Right.
Those big fans.
Yeah, and if there is a particular concern from a client, definitely in your design process, you can beef up insulation,
Yes.
Bigger mufflers, that sort of thing. So definitely you can work around noise concerns for sure.
Absolutely, yeah. It's a combination of extra insulation, like you said, and then just maybe a larger and more powerful silencer or muffler.
And what about all the black smoke that's going to be pumped through the community? Is that a concern?
Well, the beauty of burning natural gas, I mean, if you've ever lit a pilot light with a typical
Any
lighter,
furnace, yeah.
Exactly, right. There's no black smoke.
Yeah.
That black smoke you're seeing is typically sulfur and diesel, and there's no sulfur in pipeline spec natural gas. At least there shouldn't be.
Yeah, and if you do see black smoke, it's not burning properly. So if that goes for your chimney or hot water tank at home, like call a service technician for sure.
Exactly. Yes. So Aaron, there is no black smoke.
Perfect.
Yeah. Good question.
So I just want to ask on behalf of the viewers, so reliability. I know we touched on a bit, but basically we're utilizing natural gas as the fuel source to produce electricity on site. So the reliability of not being 100% dependent on the grid. So when a client does invest in this technology, they are still connected to the grid, but their costs would be reduced, correct?
That's correct, yes. So one of the things I'm always discussing with my clients is this is not becoming the primary system, as in like there's always a redundant system. This is it's an economic opportunity. It's not the primary system. Now it can be if necessary, but most CHPs like Red Deer College, they are still grid connected. So if this CHP goes down for maintenance, they're still grid connected. If the CHP goes down and they're not producing heat, they still have the boiler capacity.
Right.
So it's completely redundant. And you're taking advantage of the cost savings and sustainability benefits versus taking your facility off the grid per se.
Excellent. And you did touch on this, the maintenance portion.
Yes.
So obviously this is an engine, it has to be maintained. So that's rolled into the purchase agreement depending on the project, correct?
Yeah, it really does depend on the commercial arrangement. And we haven't really got into that, but you might say, Matthew, I see the benefit of CHP, but I don't want to own any of it. I just want to see the benefits. And so we could come in and take complete care of it. So supply and work with Aaron and his team and other great installers and build this and just take care of the maintenance and charge a per kilowatt charge. Or you may say, no, I actually want to own that and do maintenance myself. And so we can support in a lot of different ways. But one of the things we do look to do with a CHP client is establish a long-term service agreement with, or LTSA is kind of the acronym that people use, so that we're taking care of that engine. Think about your car. Think about how often you take it in for an oil change and you got things serviced. Think about if you ran your car 24/7. Think about how often you need to be taking it in, how frequent you need to be doing that. Well, that's what we're doing here. We have a big, big car engine running on natural gas, not gasoline or diesel. And so that routine maintenance, routine checks is something that needs to be considered. And that's very important aspect of CHPs.
Excellent. And obviously, depending on how well that equipment was serviced, what is the expected lifespan? And of course, this depends on the project, but typically lifespan of these engines and these systems.
Great question. So we build all of our, when I do a maintenance schedule, I base it off most likely a 10-year period, but these generators can run 20, 30, 40 years. We have generators that have been running for a very long time. And it comes down to, like you said, it comes down to maintenance. At certain points in that maintenance, we're effectively going to rebuild the engine. We'll do a top end overhaul or a complete overhaul. And we'll effectively almost rebuild that engine, but everything else still works. The alternator, the heat recovery equipment. And so to answer your question, these generators could easily run 30 years.
Excellent. And I know, again, depends on the project,
Yep.
but purchase cost or payback periods, what are we looking at as of today? What are you seeing?
That's a great question. And it is subject to so many variables, but in my opinion, a good project where I say this is a feasible project, I'm looking for a payback period somewhere between 5 and 8 years. That's a good range for me. And then to put a budget is quite difficult because every installation is different. The equipment might be similar. 1 megawatt here and a 1 megawatt there might be the same cost of the equipment, but the installation cost could be dramatically different. But no, like I said, we're looking for that. A really ideal project is 5 to 8 years. I think that's what I said. Mm-hmm. And then an okay project would be somewhere between 8 to 11 years. Yeah, so that's probably the economic windows I'd be looking for in a good feasibility study.
Yeah, and that makes sense. And that totally depends on how much of that CHP can use its heat to offset in that property. So it totally depends on what type of facility we're looking at. So exactly. that makes sense for sure. One thing that I was thinking about is the energy purchasing side. So obviously in Alberta, we're a deregulated market, mm-hmm. which means you can shop around for your power, fuel. So that's definitely something to consider when you're looking at CHP, because if they've purchased a block of energy from the grid, they got to make sure if they all of a sudden take that offline with a CHP, they don't get penalized and have to pay for that. Have you come across that? And what are the certain things we check for when we go into a project?
So in Alberta, your wires charge is set at the single largest electrical draw across a 15-minute period. That's called your ratchet rate. And I'm not an expert on this area. There's some very intelligent people here. But effectively, if you are going along at 1 megawatt of power consumption, and then suddenly for a 15-minute period, you jump up to 3 megawatts, the wires charge of your utilities cost, so the cost of transmitting, it's going to be set at that 3 megawatt mark, not the 1 megawatt mark you're at. So you can install a CHP, and it might take you a little while to realize those savings. You also might be tied into, depending on how new your facility is or how new your contract with your lines provider, whether that's Fortis or ATCO or Equus or someone else, you might be tied into a contract and you might have to buy yourself out of part of that contract. That's something we can help you with and help you determine as well. So that's your wires charge, but then there's your energy charge, where you've got a contract with NMAX or Direct Energy or someone like that. And now, again, I'm not an expert here, but my understanding is it's a lot simpler to be able to get out of that than it is your wires charge. So there are some things to be considered there. They're not roadblocks, as I call them.
Mm-hmm.
They're hurdles, something to consider. So that's kind of the energy consumption side of things. Now, the second side, and I want to actually show a slide.
Yeah, for sure.
So what a lot of people don't realize in Alberta is that power is traded almost just like shares on the New York Stock Exchange. Power is actively traded on a I think it's on a 15-minute interval, but don't quote me on that. But what you're seeing here is power prices of 2019. This is what power was traded for at the pool price. And it kind of oscillated down here in that $30, $40 range, as high as $1,000 a megawatt hour.
Wow.
It can't go above 999. And I've been told that the reason why Alberta power prices can't go above 999 is because when this system was originally made, it was writ on DOS operating system, and DOS couldn't handle 4 digits. So I don't know if that's true anymore, but that's why power prices are limited from a trading perspective up to $1,000. Anyways, why am I showing this? Because when you are a small producer of power and you meet the micro generation regulations, this is a set of regulations set by the AUC, I believe, allows you to export power onto the grid, and you can actually actively trade and sell power at the market rate. And so this is another way that you can make CHP that much more lucrative. There's a lot of complexities to this, but we can help you realize this other opportunity of not just saving utility costs, but also becoming another form of revenue for your facility.
Excellent. And that obviously would utilize a two-way meter, so that you would track how much power you're putting in onto the grid, correct?
Correct. Yeah. Yeah. There's a few things you need to install as part of your application to sell power onto the grid. It's not just simply you just hook up and power goes on. There's quite a process to it.
Yeah. Yeah, no, definitely worthwhile touching on this topic. And then, as we work with particular clients, going more in depth into the different opportunities with this technology.
Absolutely.
Excellent. Well, I appreciate your time here today, Matthew. And I recommend anyone interested in CHP for their property, for that stabilized or lowered utility costs, reach out to Matthew or myself to get the ball rolling for your project. I appreciate your time, everyone, and have a good day.
Thank you, Aaron. Thank you for having me.
Yeah, thank you, Matthew.
Thank you.